Some basic operations in a matrix. First, we'll talk about the transposition of a matrix. Simple definition is a matrix B is a transpose of A if the rows of B are the columns of A and vice versa. The transpose of A is unique and is denoted by A transpose. So let's see what we're talking about here. Say A is a 3 cross 3 matrix. Let's say the A is 1 3 5 7 1 2 1 1 9. Then A transpose is denoted by just interchanging the rows and columns of A. So for example, this first row becomes the first column. So we have 171 as the first row now. The second column becomes the second row. So we have 311 as the second row and 529 as the third row. This is basic transposition. And transposition can be done on matrices of any order. Transposition can be done on matrices of any order. What do I mean by that? Say B is a matrix of order m cross n. Then B transpose will be a matrix of order n cross m. Why am I saying that? Because essentially we are interchanging the number of rows and columns. So by doing the transpose, we are interchanging these rows and columns. Hence, this order will also change accordingly. Skimming through the Wikipedia definition, in linear algebra, the transpose of matrix is an operator which flips a matrix over its diagonal. What do we mean by this? This diagonal, if we carefully look at this diagonal of this matrix right here, the matrix is actually being flipped. How is that happening? Say 5 to 9 is the third column here. Now if we flip it by this diagonal, 5 to 9 will become the first row. Similarly for the second column and the first column as well. So here, this definition obviously makes sense. That is, it switches the row and the column indices of matrix A by producing another matrix, often denoted by A transpose. So for sake of convenience, I will be denoting the transpose by this. This is the transpose. This and this are the same. Let me just specify this here. This the same notation. So we are done with transposition. Now let us talk about some special matrices, namely symmetric and skew symmetric matrix. So symmetric and skew symmetric matrices. So what is a symmetric matrix? A symmetric matrix is just A transpose is equals to A, and a skew symmetric matrix is just A plus A transpose is equals to 0. Now let us take some examples. Example of a symmetric matrix. The example here is 1 1 1 0 0 0 0 0 0. Now clearly, if you transpose this matrix, say let me call this I for the identity matrix, then I transpose will clearly be equal to I. Now let us take an example of a skew symmetric matrix. Skew symmetric. Example. For a skew symmetric matrix, the diagonal entries are always 0. So if this is 1, this will be minus 1. This is 2, this will be minus 2. If this is 3, this will be minus 3. Now clearly you can see, let's call this matrix A. You can see that A is equals to minus of A transpose. So these are some popular examples or some common examples of a symmetric and a skew symmetric matrix. If you just skim through the Wikipedia definition, in linear algebra, a symmetric matrix is a square matrix. Yes, this is very important. For a matrix to be symmetric and skew symmetric, it has to be a square matrix. That means the order must be equal. That means M is equals to N, or we have a matrix of square order. We cannot have a rectangular symmetric matrix. That does not make sense right now. So is equal to its transpose, and this is the same condition that I told you, because equal matrices have equal dimension, only square matrices can be symmetric. This is very important. Similarly, we had the definition of skew symmetric matrix just analogously right here. I know I don't have the Wikipedia right here, but it's the exact same. Now let's talk about addition of matrices. How do we add to matrices? Addition of matrices, for the first criteria is the order must be equal. The order must be same. You cannot add matrices which have different order. So what do I mean by that? Well, if I'm saying A plus B is equals to C, and A is a matrix denoted by Aij. Now, this addition also means subtraction, so I'll just write that. Addition also, like, the same rules apply for subtraction. So remember this from the last video, this writing format. If you don't, just check that video out. So now what I can say is that Cij is equals to Aij plus Bij. So a smooth representation, let's just take an example. Let's take an example for 2 cross 2 matrix. Let's say this is 2 3 1 0 plus 1 1 1 1. So this is 2 plus 1 is 3, 3 plus 1 is 4, 1 plus 1 is 2, and this. So this is the output. So this is Aij, this is Bij, and this is equals to Cij. Plus and minus actually, because you can even subtract similarly. So addition of matrices is also done. Now let's talk about scalar multiplication. It is actually very similar to addition. So if I say lambda A, lambda is a scalar, and A, say for the sake of simplicity, is a 3 cross 1 matrix right now. So that means A11, A12, A13. So then lambda A is nothing but the individual elements multiplied by that scalar. I hope that's clear. Now this, so for example, now if it's a 3 cross 3 matrix, say A is a 3 cross 3 matrix, say 5, 1, 2, 1, 0, 1, 3, 1, 9. Now if I'm saying 3a, then I essentially mean A513, 101, 219. And if I'm multiplying 3, then I just have to multiply one row or one column. So I'll just multiply the first column. So this will be 15, 3, 9, 101, 219. This is what I mean by scalar multiplication. Scalar multiplication, only one column or one row is multiplied by that given scalar right here. Now let's move on to matrix multiplication. Matrix multiplication in very simple terms, it's just row by column multiplication. And the orders must be in a certain format. What format am I talking about? So say if A is a M cross Mn matrix and B is a certain matrix, then for the product AB to make sense, B must have order like this, M cross B. B can be any number, but N must be the same as this. So what am I saying here? I'm saying that the number of rows of B is equals to the number of columns of A for this matrix multiplication to be possible. Now clearly observe here what is happening. This is a diagram I've taken from Wikipedia. And what is going on here? Let's just try to understand. So these are the first three elements, A11, A21, A31. These are multiplied by these corresponding elements and added. And this becomes the first element here. This is this. Now similarly, we multiply this by this. And this becomes the second element here. And correspondingly the other elements. Let me take an illustrative example to just finally clear this. So for example, let me take a 2 cross 2 matrix, 2, 1, 3, 1. Multiplied, this is a 2 cross 2 matrix. So remember, I need the number of rows of the corresponding matrix to be same. So let's say I take a 2 cross 1 matrix. So let's say 3 and 5. So I can clearly guess that the product matrix will actually just be a 2 cross 1 matrix. Why is that? Because these get ignored. And these become the final order. So 2 cross 1. Now if I multiply 2 multiplied by 3 plus 1 multiplied by 5, that is 11. 3 multiplied by 3, that is 9, plus 1 multiplied by 5, that is 5. So 9 plus 5, that is 14. And that is how matrix multiplication is done. To cover up, there are some extra properties that we must know about of matrix multiplication and transposition. This is known as the associativity property. Associativity. What this means is that if ABC is a product, then AB, if I multiply AB first, then that is the same as multiplying BC first and then multiplying with A. Secondly is the transposition property. That means that if I'm taking the transpose of a product, I can open this as B transpose A transpose. And if it is A, B, C, D, up till say E matrix, let's say there are 5 matrices, and I take the transpose, then the transpose is given as E transpose, D transpose, C transpose, B transpose, A transpose. Essentially reversing the order and taking transpose and multiplying. A third very important property is matrices, in general, are not commutative. What do I mean by that? What I mean is that for a general matrix A and for a general matrix B, AB is not equal to BA. We cannot say this directly. May happen. This may happen, but doesn't happen always. So that's it for this video.